Hi everyone, welcome to the deep learning workshop. In this video, I will go over the transformer model, especially for the machine translation task. Before we look at the machine translation task, it's important to understand different ways we can use the transformer architecture. So at least there are three main ways to use the transformer architecture. Um, the first way is to use only the encoder of the transformer model, um, and typically some classic examples are BERT or Roberta models, and it's used mostly for text classification tasks, or sentence classification tasks, question answering, and so on. The second mode of usage is decoder only usage, where we only have the decoder component, we don't have the encoder, and typically we use it for language modeling task, trying to predict the next word given the previous set of words, um, and and then the learned model can be used for open-ended generation or even solving problems like autocomplete. The third and the final usage of a transformer block is encoder-decoder based, where we have both the encoder and the decoder. And a classic example is machine translation, where the encoder consumes the source sentence and the decoder outputs the target sentence one token at a time. And in this video, we'll focus mostly on the last use case, which is encoder-decoder. We assume we have both encoder and decoder and try to solve the machine translation task, specifically translating a sentence from French language to English language. Right. And this notebook was tested in Google Colab, so I would strongly recommend to try this notebook in Google Colab, um, where you can actually use a GPU quite easily to um, train your transformer model. So first we'll import some necessary libraries, mostly Torch and sometimes Torch text also, which would be useful to process the data and then set up data loaders and so on. So starting with, we'll first prepare the tokenizers. So we need the English and the French tokenizers from Spacey. So we'll download that and then we'll load them and then we'll create the tokenization functions for French and English. Once that's done, now we'll resort to Torch text. The functionality is provided by Torch text to set up the data reader, loaders, and so on. So first we define the torch text field for both the source and the target, and we say if we need the end of sequence token, we want to set the lowercase to be true, and importantly we pass the tokenization function which we just created. All it's taking is a piece of text and then using the corresponding language specific tokenizer to output a list of tokens. And for the dataset, we recommend going to this website and downloading the English and the French dataset. And then you can you have the train dev and test split, and you can actually like load all of them using the tabular dataset method. Be sure to specify the right column names. So the first one could be the English in the file. So you have to use that as a source. And the second one is actually the French. So, or it's the other way around, right? So you can check the file. So you ensure that the fields correspond. The first column is English, and the second column would be the French. So since we are doing French to English, we have to first say target and followed by source. and we can print the number of examples in each of the split. We can even just print some sample examples, and then we build the vocabulary. The only constraint we are setting on the vocabulary is that the word should, the token should at least occur twice in the corpus, training corpus. And then we can look at the index for the pad token, and then we can set the bucket iterators, which is going to do a lot of heavy lifting in terms of padding, creating the padding and all that, right? So different sentences in a batch can have different lengths, and we need to do padding, and padding might be tricky depending on the batch size of the batch. And bucket iterator basically abstracts everything out, so you can readily use them, and you can even test it out by uh, iterating over the iterator and printing a batch and checking the size. If you check out the size, it would generally be, for the source, it's generally the sequence length followed by the batch size. So the batch size is 16, the sequence length is 20 for the source. And similarly, the batch size is 16 for the target, and then the sequence length, the max sequence length is 21 for the target. Yeah, so once that is done, you can save the vocabulary somewhere, and then we can look into the NN.transformer module, which has the implementation of both the encoder and decoder, including the multi-head self-attention, feed-forward net, residual connection, and layer normalization, and so on. The only thing which is actually left out is the input token embeddings, the NN.embedding layer for that, and then the positional embeddings. Yeah, and then creating the mask for the source and the target. Otherwise, it's really easy to use. The NN.transformer already asks us to specify the number of encoder layers, number of attention heads, hidden size, number of decoder layers, the dimension of the feed-forward net, and then the dropout value. So since it is doing all the heavy lifting, all we need to do is create the token embeddings. We can use NN.embedding for both encoder and decoder to create the embeddings. And then we can, once the embeddings are created, we can then create the positional embeddings. So we already saw two methods to create positional embeddings, either using static way, using sinusoidal embeddings, or the learnable way using learnable embeddings from the NN.embedding table, right? So we are using the latter here. It's generally empirically better, so we go for that. And then we try to create the mask, which is the last left out thing. So here we can just try out some dummy positional input and see how the positional embedding are like. And so that's something which is here. And so pass some dummy positions, and eventually we want to aggregate the token embeddings with the position embeddings using additive sum, right? And then we create the binary mask for the source tokens. So for the source, we want to ensure where the padding tokens are there. So we can easily create that by using the corresponding index corresponding to the pad, right? And once that is done, now we are all set to create our transformer model. So we can call NN.transformer. It's going to take all the values which we discussed previously. And for the exhaustive list, I would strongly encourage to go to this URL and try to understand what are the other parameters which the transformer model is taking. And now we can print the transformer model. You can see the encoder and the decoder. Yeah. Right, so and the different layers. So each encoder and decoder has two layers, so you will have two layers basically. And note that the decoder has two multi-head self-attention, multi-head attention. One is a self-attention, other is a cross-attention. Right, where the attention for the encoder. And right. So once that is done, then we can create the target mask. So when we are generating the translation, we can only afford to look at the past and the current tokens. not the future tokens. So we want to ensure that the model never looks at the future tokens while computing the self-attention logic. So that's, we can call the generate square subsequent mask function to create that, right? So it's very convenient. Once we have all of that, then we can readily look at the transformer class. The transformer class has the nn.transformer module, and then the input embeddings, and then the position embeddings. And then the forward functionality, which is the code, it's quite simple. We have the source and the target. So first we compute the position embedding for the source. So for that, you will create the source position, and then you pass it to the um, position embedding layer, and then you do additive sum with the token embedding layer, and then you compute the dropout. Similarly, you do it for the target as well, right? For which you also create the target position before. So once we have combined both the position embedding and then the token embedding, now we can actually do the encoding part and the decoding part. For the encoding, all I would need, I mean, it's done together. So all I need to give is create the mask for the source and the target, and then provide as input to the self-code transformer. And then the decoder is going to give me an output, which is going to be for each token in the target, it's going to give me a probability distribution over the target vocabulary. So using which I can always pick up what the token is, right? And once, yeah, so this is the forward propagation logic, and after this, everything else is straightforward. We define the hyperparameters for the model, and then we create an instance of our own transformer block, transformer class, and then we define the train and the evaluation logic. The training is fairly straightforward. We set train flag to true, and then we iterate over the training data set. We create the batch, we clear the gradients, and then we pass the examples, the batch to the model, get the output, and from the output we try to predict the target, and then we compute the loss, and then we do backward, and this would compute the gradients. And before updating, we can do a gradient clipping, and then optimizer.step would update the gradient instantaneously. The inference function is basically going to compute the blue score. So we create a tabular data set over the evaluation set, and then we set the eval to be true, and then we pass over the test examples and create a batch, and we pass it to the trained model, and then we start like inspecting the output of probability distribution, and we start recording the tokens, and we get the token indices and convert them into strings, and then we call the corpus blue function, which is going to give us the blue score. That's the popular metric for evaluating machine translation model. And then we can also evaluate based on the loss alone, so feel free to check it out. And then this is the binding logic, which combines training, evaluation, and so on. This training is going on for 15 epochs, and then we also try to print the train loss, train perplexity, validation loss, validation perplexity, and then the validation blue. And finally, we choose the best model and then try to compute the test blue. So here is the kind of the learning curve in the raw format. You can always try to visualize them as a learning curve to better understand how the learning is happening. Yeah, so the model is probably learning. It's reaching up to a test blue score of 46.9. Yeah. Yeah, I think that is mostly it. I recommend these references also if you want to get more context about what is covered in this tutorial. If something is too abstract, you can always check into one of these links to get more context. Thanks a lot for listening. Cheers.